classes. If you feel disturbed by how quickly all this stuff moves, then you can thank the high lords of engineering who decided to put 2 classes into one for you for your entertainment. What we're going to start with today is an example that we're going to use to bring in a bunch of ideas that we've talked about previously. I'm going to be asking questions. I'm going to be cold calling, which means like the shiftier you look, the more likely you are to be cold called. So if you're sitting there looking strong and confident, you'll probably I'll probably ignore you. Or you could raise your hand. That's another thing you could do. So we're going to start with, I'm going to write down a problem. So I'll give you some vectors. V1. While I'm writing these, I will add that because I blew the recording of the last class, I haven't had a chance to re-record it. I'm going to re-record the lecture in my office by myself with my Blackboard. So I will post a video of the previous lecture. I apologize for screwing it up. 1, 2, 7. And V3 is 1 minus 2, 3. Okay, question 1. I ask, is this set of vectors linearly independent? So the question I've got that I'd like answered, the question that I would like to have answered here is, what does it mean for a set of vectors to be linearly independent? The clue that I'll give you here is that there's an equation that you need to look at to decide if that's true or not. So what I'm looking for the answer here is not how to use a row reduction to do it. That's a follow-up question. But what does it mean to ask if that set of vectors is linearly independent? What equation should I be writing down?
C1v1 plus C2v2.
Okay, so we're going to check this equation. So we're going to check C1v1 plus C2v2 plus C3v3 is
0.
Equal to 0. And what am I looking to see? What would it mean for these to be linearly independent? How would I know this from the equation?
So if that's true, but in C, like they're not equal to all equal to 0.
So that's linear dependence. David.
Would it be that the sum of 2 vectors equals 1?
Okay, that's actually equivalent to the linear dependence condition here.
The only solution.
The only solution
is that all of them equal to 0.
Okay,
Like
so
C1, C2, C3.
yeah, if the only solution is C1 is equal to C2, which is equal to C3 is equal to 0, then the vectors are linearly independent. Independent, which means no vector can be written as a combination of any of the others. Now, the condition that Sarah gave us, where there's a solution that are not all 0, there's some way of combining these vectors together to get the 0 vector out, where they're not all 0. If C1, if there is a solution where C1, C2, and C3 are not all 0, then we're looking at linear dependence. So linearly dependent. All right, second question. So the definition part of this is important. If I ask you if a set is linearly independent, we characterize that by looking at the solutions to this equation, the scalars C1, C2, and C3 that solve it. How do I actually do it? Now I've given you concrete vectors. This is sort of the abstract setup. I give you 3 concrete vectors. What do I do with them?
Put them into a matrix.
So we got one tool. So we bring out the hammer and we put them in a matrix. 1, 1, 1, 0, 2, minus 2, 5, 7, 3. We row reduce it. 1, 0. I have actually what this row reduces to right here. 2, 0, 1, minus 1, 0, 0, 0. What do I conclude? Why? Angel.
I forget which one's dependent.
What should I be paying attention to in the matrix? Maybe let's make the question more concrete than that.
The bottom row with zeros.
Ah, okay. So That is going to be an answer for a future question, which is, do the vectors span all of R3? I'm asking that, but I'm asking a question about the columns of the matrix because the vectors form the columns of what I started with. So information about the columns is what I'm after here. Hold on, I know you like. Let me get somebody else. Yep.
Two of them are pivot columns.
Okay, so pivot columns. This is a pivot column and this is a pivot column. They have pivots there because they have leading ones. So there's two ways to interpret that. The first is exactly to this question. Because these are both pivot columns and there is a free column, what was the conclusion? Did you say what, like, that's what I should be paying attention to. What is my conclusion? Two of the columns are pivot columns. You have an answer to that one, Sarah?
Yeah, it's linearly dependent.
It's dependent. So not every column is a pivot column. Not every column is a pivot. So V1, V2, and V3 are linearly dependent. All right, I'm going to ask another question. Can you tell me how, if they're linearly dependent, I should be able to write one of the vectors as a combination of the others? How do I do it? David?
Is it 2v1 plus negative 1 v2
Equals?
v3?
Yeah. So you can read that off the matrix. So if you look at the matrix 1, 0, negative 2, 0, 1, 1, 0, 0, 0, as the row reduction of what we started with, 1, 0, 5, 1, 2, 7, 1, minus 2, 3, if I had thought about this original setup here as the question where I put an augmented column right here, that would be asking the question, can I write the third vector as a linear combination of the first two? That's what putting that augmented column there would have asked. Can I write this as this vector as a combination of these? And the answer is yes. And in fact, the way you would do it would be minus 2 times v1.
Hang on, that should be a positive.
Positive 2, negative 1. 2 times v1, thank you, plus negative 1 times v2 is equal to v3. That's easy enough to verify. Generally, I like it's not a bad idea to just verify when you're looking at these things that you've actually got them correct. 1, 2, 7. So 2 plus negative 1 is equal to 1. 0 plus negative 2 is negative 2. 10 minus 7 is 3. So the combination works. Okay, how do we interpret what we've done here? The idea is I can think of, in a non-unique way, I can think of the vectors v1 and v2, the pivot columns. The original vectors form a plane, geometrically. And the third vector sits inside that plane. There's not any new direction happening there. I have v1 and v2 point in different directions, and v3 is a combination of those, and so it's trapped in the same plane. That's why we have the sort of linear dependence here. What would happen if I had written the vectors in a different order? What if I switched, in my original problem, what if I had switched these two? What do you think would happen? Hassan?
It would just be 1 v2 is equal to v3.
Well, you'd possibly get a different row reduction. Would you get a different number of linearly independent vectors? No, because they still form a plane, right? Like is the idea. So the row reduction could change if you switch the two, right? Because you wouldn't stop at this as the row reduced form because you would need a pivot in this column instead, right? So you would change the combination is essentially what the answer would be. Okay, so now we're going to get to Angel's point earlier, which is I'm going to ask another question about these vectors. Do v1, v2, and v3 span R3. Now before I'm not going to ask you to interpret the matrix yet because the definitions are important in what we're doing here. What does it mean mathematically? What does it mean to span? What am I asking when I ask do V1, V2, and V3 span R3? Yes, the way we answer the question was with a matrix reduction, but what is the actual question we're asking?
I can get any vector in R3 by adding multiples of V1, V2, and V3 to each
Okay, so what would the specific thing I'm trying to write? So can you by adding multiples, what's the actual equation I would write down?
C1, V1
Is C1 V1
plus C2 V2
plus C2 V2
plus C3 V3
plus C3 V3
equal to matrix ABs.
Okay, so V, is that always consistent? If I was going to write that down in terms of the actual things that we have here, I'm asking the question, is C1 times 105 plus C2 times 127 plus C3 times 1 minus 2, 3 equal to A, B, C, always consistent? If it is, every vector in R3 can be written as a linear combination of these. If it's not, some vectors can be written as a linear combination of these, but not all of them. How do I check? Here you go, Angel, you can answer the question now. How do I check?
There's all zeros at the bottom, so there's nothing.
Yeah, so there's a row of zeros here. So what will happen is, if you actually put this into its matrix form, so if you took this particular equation and wrote it down in matrix form, it would look like this. So you could write down 105, 127, 1 minus 2, 3, A, B, and C. And when you row reduce this, you're going to get the same matrix that you get when you row reduce this. The columns don't change with row operations. So if this matrix row reduces to this, in the augmented matrix, it's going to row reduce to the same thing. 1, 0, 2, 0, 1, minus 1, 0, 0, 0. And then over here is going to be combinations of A's, B's, and C's. Right? I can't actually write the functions down because I'm not going to go through the row operations, but there'll be stuff over here that's algebraic combinations of A, B, and C. So, to be a spanning set like this is to say, no matter what you choose for A, B, and C, the equation can be solved. And what will happen is, I'm going to be able to pick values of A, B, and C that make this not work. So, it is possible to have a pivot in the augmented column. Which means it's possible for that equation to be inconsistent. All right. So now I'm going to give you a more abstract version of the same type of questions. We'll keep driving into this stuff. Ugh. Okay. Suppose instead I tell you that you have a set V1, V2, V3, V4, and V5. All of these vectors are in R3. Which is to say they're all three-dimensional vectors. And I tell you that this matrix row reduces to this one. Okay, so that set of original vectors is row equivalent to that matrix right there. Question 1. Does the set V1, V2, V3, V4, V5 span R3? Can I write anything in R3 down as a combination of these vectors? Dimitri?
Yes.
Why?
Because the pivot in A, B, and C.
Yeah, there's a pivot in each row. And that means no matter what I stuck over here, it's impossible for there not to be It's impossible for there not to be. It's impossible for there to be a row of zeros with something that's not zero here. I can never have a pivot in the augmented column. So if I stuck an augmented column in, I just have it, right? So the answer is yes. All rows are pivot, which means AX is equal to B is always consistent. Always consistent. Second question, is the set linearly independent? Aiden.
Which one?
This Aiden. I'll get you next. I'll go through the Aiden pile.
No.
It's not linearly independent? Is it linear? I'm actually going to pin you down.
Okay.
Is it linearly independent or linearly dependent? And why?
Last time I kind of got caught up on which, because I know that like the
Independent I'll just briefly. Independent means no vector can be written as a combination of any of the others.
That's what independent.
That's
is?
independent means
Okay, then I'll say it's dependent.
that this is dependent. So the claim is it's dependent. Do you have a reason why?
Because some of the vectors can be written as combinations.
How do you know?
Well, if I were to write that out in the
What if like, you know, like what are you looking at in the matrix that's telling you that? You're answering a harder question than I'm asking you. What are you looking at in the matrix that's telling you that there must be dependence here?
Well, not all the columns have a pivot.
Okay, there's free columns, right? There's free columns, right? That's essentially what you're driving at. Okay, so because there are free columns, that means that it must be the case that some vectors are combinations of the others. Do you know which vectors are combinations of which? This is actually sort of a harder question.
Yeah, V3 is 2V1, and then it looks like
Yeah.
5 is like...
So I'll show you the easiest way to do this. If you did that, that tells you that V3 is 2 copies of V1.
Yeah.
If you did this, so now you gotta pretend that this isn't here because it's not contributing anything, right? That tells you that V5 is 1 V1 and a V2 and a V4, right? Because if you cover that column up, the matrix that's left tells you which vectors combine. Yep.
So it only depends on the pivot?
The pivot columns tell you everything else that's happening, yeah. And you're allowed to just sort of, remember, the matrix row reduces the same way if you delete columns. All of the rest of the columns row reduce exactly the same way it did before. So this is an example of a set that spans R3, but is linearly dependent. So now I'm going to give you a different question. Sort of the converse sort of thing. What if I had vectors V1 and V2 in R5, and their matrix row reduces to this? That's possible. Those are both vectors in R5, and they row reduce to this. Does that set of vectors span R5? You should already be suspicious that 2 vectors could somehow span a 5-dimensional space, right? So, or if all you know about is matrix algorithms, you might look at that and say, I've learned about rows of zeros, and I see lots of rows of zeros here, right? Every one of these places is a place where a possible entry could be over here that would put a pivot in an augmented column. In fact, it's going to be quite difficult for a vector not to put a pivot in the augmented column, right? So these clearly don't span R5. Rows of zeros means that they don't span R5. Are they linearly independent? Why, Owen?
Because there's a pivot in every column.
Pivot in every column. Pivot in every column means the set is a linearly independent set. So this is a set of vectors that does not span, but is linearly independent. All right. So generally when you're approaching these problems, these are the sort of like techniques that we use to analyze sets of vectors, right? We take vectors, we cast them in the language of matrices, we row reduce, and then we just have to interpret what the matrix says at the end. So one thing that's kind of interesting here is that this is actually where our notion of dimension comes from. So when I look at this set over here, and I think I've got two linearly independent vectors. Yeah, they live in R5, but I've got two linearly independent vectors. What sort of linear space do they make? Geometrically, two vectors make what?
R2.
A plane. They don't make R2 because they live in R5, right?
Like
They sort of look like a
space in
version
R5 that
of
is
it's a
R2.
two-dimensional subspace of R5, right? So R5 is this big, impossible to understand thing, but living inside of it is this flat two-dimensional plane. Why is it two-dimensional? This is the dumbest possible definition of dimension you come up with. Because there were two pivots. Two pivots means two independent directions, which means dimension. These two vectors together make a two-dimensional space. How about these vectors? A three-dimensional space. They span all of R3, and they make a three-dimensional space. So the sort of naive way of identifying dimension is, you can think of, if I have the number of linearly independent vectors in a spanning set, it's called the dimension of the span. So I got a bunch of vectors, I pile them up in all possible ways. The number of the maximal sort of number of linearly independent vectors you've got tells you the dimension of what you made. I'm going to make this more concrete in a second. So I'm going to go back to this thing that we started with earlier. So we had that set of vectors. I'll talk a little bit about that one specifically. So that was V1 was 105. V2 was equal to 127. V3 was equal to 1 minus 2, 3. So I'm going to make the following claim. We showed earlier that 1, 1, 1, 0, 2, minus 2, 5, 7, we didn't show, I just told you, that this row reduces to 1, 0, 2, 0, 1, minus 1, 0, 0, 0. There's two pivot columns, here and here. So what that means, if we sort of feed the idea of linear dependence into all this, this told you that V3 is a combination of V1 and V2. And so the argument I'm going to make is what that means is that the span of V1, V2, and V3, the set of all possible linear combinations of V1 and V2 and V3 is the same as if I just chucked the V3 out. If these guys formed a plane together and that vector lives inside of it, then these also, I didn't change the plane by throwing a vector away. I haven't taken any information away. That V3 already lived in the plane that was created by V1 and V2. So the claim here is that actually the span of V1 and V2 and V3, the span of V vectors, notice that when you did that, when you took the V3 away, the vectors that were left are now linearly independent. If you just ignore this column, and you'd written down the matrix for those two vectors, it row reduces to this. 1, 1, 0, 2, 5, 7 row reduces to 1, 0, 0, 1, 0, 0. There's a pivot in every column. Those are linearly independent. So the observation is the set V1, V2 is a linearly independent spanning set for the span of V1, V2, and V3. These were the vectors we used to build the space, but I didn't need all of them. I could throw one away and keep the same span, and I've got the added virtue that the thing that I ended up with is a linearly independent spanning set. And this idea is so important. The idea of a linearly independent spanning set is so foundational to linear algebra that we give it a name. Okay, so it's our first formal definition here today. So definition: if S is a subspace and V1, V2 up to Vn is a set of vectors in S with 1, S is equal to the span of those vectors, and 2, the set V1 to Vn is linearly independent, we say V1 through Vn is a basis for S. The notion of a basis is foundational to linear algebra. A basis is a linearly independent spanning set. Basis is a linearly independent spanning set. And the reason that we want that is if my spanning set is linearly independent, every linear combination is unique. So for example, the vector 1, 0 and the vector 0, 1, that set is a basis for R2. It's called the standard basis for R2. Every single vector in R2 can be made by multiplying by this by x and this by y, and what you end up with is xy is equal to x times 1, 0 plus y times 0, 1. A basis for a space is a set of vectors that I can construct everything out of those vectors, and I can only do it in one way for each vector. The vector 2, 3 can only be written as 2 times this vector plus 3 times that one. There's no other way I can rig them together to make 2, 3 come out. Okay? So a basis is sort of like, you think of it as the skeleton of a vector space. The minimum information that you need to recover it. I will point out, they are not unique. They're highly not unique. So, for example, if I wrote down something like the vector 2, 3 and the vector 3, 2, so there's V1 and V2, and I ask, is that a basis for R2? Is V1, V2 a basis for R2? Well, we've only got one tool. So what are we going to do? Well, what you do on every one of these problems, you put it in a matrix, 2, 3, 3, 2. You probably already guessed, this row reduces to the identity matrix. So if you're checking to see if something is a basis, you need 2 pieces of information. Does it span R2? Kieran, does it span R2?
Yeah.
Why?
It's not all zeros.
Good, yeah, pivot in every row. Is it linearly independent? Aiden, second Aiden. I get to the third one eventually.
Yes.
Why?
Because if you like multiply one by like your scalars,
I want a dumber answer than that. How do I know by looking at the row-reduced matrix that they're linearly independent?
it's just pivot.
Pivots in every column. Pivot in every row means that it's a spanning set. Pivot in every column means that it's linearly independent, so it's a basis. So it's linearly independent because it's all pivot columns. It's a spanning set because there's a pivot in every row. So a linearly independent spanning set is a basis. Yep.
I think you already answered this, but like if there's a 3 vector, then you
Ah.
can't say it spans R2 because it could be pointing in a different plane.
Okay, so if I put a third vector in the pile?
No, like it's a 3-dimensional.
Ah, okay. So it doesn't. So that's that. Basically, what you get there is a basis for the subspace that they create, but not all of R3. So let's actually do exactly the same setup, but let me put a third slot in here to clarify the question. This is actually this is a really good question. Let's look at V1 is equal to 2, 3, 0. Is this the question? The setup you're after here, like a third slot?
Yeah, like does that
2 vectors in R3, right?
Yeah.
Okay, so if we let S be equal to the span of V1 and V2, if that is the space that I'm considering, it's just the span of those 2 vectors, and you start with this, so sort of by definition, these must be a spanning set because the span of a spanning set is the space, right? So automatically these have to be a spanning set.
Yeah, but that's the actual vectors. If you only had the row reduce, you wouldn't know.
Well, because you don't know you're exactly right. You don't know the vectors you don't know the directions they originally came from. You would know that those 2 vectors formed a plane, but you would not know what direction it is. You have to have the original information to conclude anything about what's happening. The original vectors would tell you what the plane was. This would row reduce to 1, 0, 0, 1, 0, 0. So that tells you, yeah, these vectors are linearly independent, and they definitely span their span. So you could conclude here that V1 and V2 are a basis for S. They're a basis for their span, but they're not a basis for all of R3 because they don't span R3 because there's a row of zeros.
No, R2.
And yeah, you can't
say
okay.
R2.
So what you're driving at is actually the single most important idea of linear algebra that I can't tell you about. There's no time for it. If you were taking 206, we'd have weeks to talk about this. You're talking about the idea of what's called coordinates. So I can cheat and think about this space as R2. I can do that. It's a 2-dimensional plane because I can say, well, every vector inside this space is a linear combination of this and that. How do I get those things? I wasn't going to talk about this today, but I was going to talk about this next time. So it's worth seeing. So if I did C1 times 230 plus C2 times 320, that's all the possible linear combinations, right? If I understood that I was working just with vectors that I built out of these, I could write this as a vector C1, C2, as long as I indicated down here that I was working with respect to some basis. The particular basis that I'm working on is this basis. And all I'm telling you is the coefficients to multiply by those things, right? If you tell me these numbers, what do I do with them? I multiply by them by those 2 vectors and I recreate it. From a mathematical perspective, though, I've taken this 2-dimensional subspace of R3 and I've just sort of started thinking about it like it's R2 instead.
But you're just basically saying that like if this is R3, then you have a plane that's diagonal, and you're saying that it could lay on the flat.
Yeah, you could. You could just think about it as laying on a flat plane instead, right? So the mathematical word for this, for those of you that will come across this in the future, you don't need to know this. This is called an isomorphism. And the idea is every 2-dimensional vector space can be thought of as R2. Every 3-dimensional vector space can be thought of as R3. There's a trick where as soon as you figure out a basis and write the coordinates down, you can just immediately not think about it as R3 anymore, as a plane in R3. You could just think about it as a flat plane in R2, right? And you can go back and forth by saying, well, what if I want to go back to R3? Just take the numbers and multiply them by the vectors, and you get right back to where you started, right? So this If we had 3 more weeks, I could teach you all this stuff. Okay. So one thing that one takeaway that you might have from this at the moment is this all seems kind of like limited if we can only talk about vectors in R2 and R3, right? So we're teaching you all this language of linear algebra, and I keep making the claim that somehow this is sort of foundational to the way that we think about all of these sort of approaches to science and engineering. So one of the ways this is going to show up, and this is not part of the course right now, right? So this is not part of this course, but I want to give you like an anchor as to where the stuff goes. So you remember when we did Taylor polynomials? It was a way of turning a function that was reasonably behaved into a giant series, right? And I could cut that series off at any point, and I would have a finite approximation for it. Like if I want a 20th degree polynomial that approximated a function, I could just calculate the Taylor polynomial and stop at x to the 20th. One of the most important ideas, maybe you could make the claim this is the most important advance in the last 300 years in the way that mathematics is used in practice, in science, engineering, and applied math, is an idea called Fourier series. So how is this stuff actually used? Okay. The first answer is all this stuff with vector spaces and the finite dimensional vector spaces, we're going to see this in the solution to second and third order differential equations. We're going to use all of these ideas when we get to chapter 8, over and over again. The bigger picture, and for those of you lucky enough to proceed into 344 or various areas of your science and engineering study, basically boils down to this. If I look at the space of nice functions, where nice is a term I will not define for you, but they're sufficiently nice. In fact, you can think about them as being periodic functions. That's actually a vector space. If I add 2 periodic functions together, I get another one. As long as they have some kind of mutually divisible period, right? A sine and a cosine make a new sort of combination of sine and cosines. So this is a vector space, and the basis for this space, the way that we could write every possible space, is not a bunch of vectors like this. It's vectors that look like this. I can build any periodic function by adding together not vectors that look like this, but sines and cosines. One of the most profound inventions of the last 300 years is the idea that I can think of a function as an infinite series of cosines and sines. Now, if you're a mechanical engineer and you study vibrations, you're going to be doing a lot of that. If you're an electrical engineer and you're going to be studying signals and control theory or RF stuff, you're going to be doing a lot of that. If you study heat in any way, you'd be doing a lot of that. Anything that oscillates, anything that moves periodically, you use this idea, which is called a Fourier series. A hell of a lot of the technology that you guys use every day is built off this idea. If you've ever used noise-canceling headphones, that comes from the idea that you can rip signals apart into sines and cosines. So, this is a profoundly important idea, and it turns out that these things, in the same exact way that I'm talking about this vector and this vector as being the skeleton of a 2-dimensional vector space, these sines and cosines form the basis for an infinite dimensional vector space of functions. So when you go on in your various fields, all of the ideas that we're learning here in finite dimensions in linear algebra can be brought to bear about thinking about functions like this, infinite dimensional linear algebra, or cutting it off and having finite dimensional linear algebra. You can basically turn this crazy study of periodic functions you think about these things as being like Taylor polynomials, but made out of sines and cosines instead of x to the n. You can cut it off and just do that. You can take this crap, as weird as this looks, you can take this stuff and turn it into column vectors. and matrices. And that kind of analysis is basically linear algebra. The same stuff we're learning right now is what underlies all of this. If you want to join me, and I'm going to sign up, I don't know for sure yet. I'm going to teach 344 if I can in the winter, and I'll be able to teach you what the hell any of this means. The idea of studying a vector space of functions. We are going to start with very easy vector spaces of functions when we start talking about differential equations. So I'm going to give you one last example to try to anchor why we're doing any of this at all for all of you guys. So if I wrote down the differential equation y prime prime plus y is equal to 0. That's how we started the class with the differential equations, right? We're going to learn a way to show that the solutions to this differential equation, two of them are y1 is equal to the sine of x, and y2 is equal to the cosine of x. You can verify that those two equations, so those two functions solve that differential equation. The second derivative introduces a negative sign, which is why they cancel out completely. Okay, so we're going to do this move. We're going to call this, we're going to think of this as a vector. And we're going to think of this as a vector. And we're going to make the argument that every solution to this differential equation, every solution has the form C1v1 plus C2v2. Well, that looks an awful lot like what we've been doing. The span of two vectors. But now we're thinking of the span of sine of x and cosine of x. The span of two functions instead of two numerical vectors, two column vectors. It's just a linear combination. The solutions to these look like a linear combination of these. So we think of it like they're vectors. What should the dimension of the solution space be?
2.
Well, that would be true if I knew what?
The size of V1 and V2.
Well, it's not the size of V1 and V2. What relationship do they need to have to conclude this is a dimension 2 space? They should be linearly independent, right? Well, damn, I don't know how to check linear independence of functions. We need a tool for that. So if you look in the book, there's this extra bit of the chapter that I haven't talked about right now called the Wronskian. The Wronskian is basically a way of detecting if these are linearly independent. So there's a condition you can use to check those are linearly independent. If they were, then we'd say, oh, the dimension would be 2. If they were linearly independent. And notice, the dimension is 2 corresponds to the order of the differential equation. So the more derivatives we apply into the differential equation, the larger the solution space gets. So one of the things we're doing that links back to what we started with is, once we have the notion of linear independence and basis and linear combinations and span, we can take all these ideas and go back and do linear algebra with it. This is why we took the detour. Okay, so what we're going to do tomorrow is, I haven't even decided if I'm going to do a quiz or not. I might just give you guys a million problems to work on to make sure we're absolutely all on the same page with what's happening now, because this is where, if you're going to die in this class, this is where it happens, is this chapter and the next one. So, like, we got to make sure everything here is concrete, because next time we're going to talk about one of my favorite topics, which is called eigenvalues. That's what we're heading into. And there you go. That's the one that you can go home and tell your mom that you learned about eigenvalues in school, and she'll think that you like came down from an alien spaceship or something. So, all right, I'll see you guys on tomorrow.